So good morning, everybody. Thanks for whether good morning, good afternoon. It's I'm calling in from our operations center in where we do our R&D and product testing in Sacramento, California. So thank you all for carving out a little time today to learn more about what we think is some very important and disruptive opportunities to dramatically reduce diesel and remote applications. And we're going to talk through a number of different subjects, and most of at least half the time is going to be Q&A to give everybody an opportunity to ask questions about things they've heard about, things that they'd like to dig deeper into, and we'll take it from there. So the structure of this will be to first talk about, kind of give everybody the same baseline of here's what the different platforms are out there, and then we'll talk through what we call the variable speed generation platform, which is ideally suited for not just diesel reduction on the diesel side when it's just engine alone, but more importantly, be able to really leverage the solar and wind power that is everywhere. So with that, Jermaine, if you can go to the next page. This happens to be a picture of the system that went into service first. Innovus Power has been around, by the way, since 2013. This system is our first installation in Aklavik, Northwest Territories. The company that operated it has been Northwest Territory Power. And this is the physical system in next to the powerhouse, and you can see in the little upper piece the solar array that was also installed up there. We'll talk more about that installation in a little bit. Next slide. So quick summary, we'll go through who we are and what the challenge as we have seen it over the years. We started traveling to Alaska and Canada roughly 11, 12 years ago. Had spent a lot of time with different organizations to make sure we really understood how to best tailor solutions that ultimately can cut the cost of power in half and well beyond that. We're going to talk about what we call the energy management control power, or any energy management centric power, we sometimes call it, versus engine control power, which is really what we've been using for 100 years, which is synchronous generation. We'll talk about the benefits and how we, in fact, we'll take you through case examples of how you can get well beyond 50%, and even we'll give you a case example of how to get to 80% reliance on renewable power. And we'll also talk about there's situations where obviously we would love to have everybody buy our variable speed generation systems with what we call our EMCS Grid Genius platform, but there are situations out there where that may not be the best solution. And we'll talk about what the alternatives are, and frankly, most of you probably already seen what those alternatives are when we talk about it. And we'll touch on remote how we manage these systems remotely and monitor them, and also what some of the field applications have been, and how the range of options available depending on the installation for each different type of installation. So next slide. So, ultimately what we're about is reducing CO2 in fuel, and really maximizing solar and wind power without curtailing it. Most of the large capacity installations in the last 15 years, where have been really wind power in Alaska, where wind power has in many cases exceeded should cover the entire demand, at least when the wind is fully is at its full force. Unfortunately, most of that capacity has had to be curtailed. So we'll talk about, when I say without curtailments, this way you can fully harvest the yields of your solar and wind installations. For us, one thing that's important for everybody to know, we have no bias to given OEMs and technologies. If you think about us relative to the picture on the right, we're about bringing in the most dependable and greenest, fuel efficient energy sources, combining them into a singular system. So ultimately, the customer sees the benefits of low cost, low CO2, high reliability power. Our markets uh, from this session is we started out in remote applications, and we applied our first system in 2018 in January. That was the one commissioned that you saw the picture of a few minutes ago. And we now, in the recent years, we've broadened into, we call it grid tied applications, where customers are looking to lower power costs or frankly, just be a lot less reliant on grids. And there is a lot of that applicability, in areas that most people wouldn't think of. So, we're in discussions with organizations or developers where they're building new communities. They have a grid and the cost of power is very reasonable. In some cases, they actually already use hydro, but there's just not enough electricity. So how do we take advantage of solar and wind power in those areas and basically um, use the grid as a secondary source? So that's what we would call a grid tied opportunity. That's not the subject of today's session. We're going to run another session on that platform either in July, probably more like August. But also, and so ultimately, so we sell systems that are grid tied, islanded. We do upfits to existing systems. So we have customers who have say natural gas gen sets that aren't performing as they hoped, not delivering the savings, not having poor power quality. So we've done upfits on. You'll see a case example. Something like that. We do operation and maintenance. The point of this is that's a core part of our business. If somebody's going to put multiple energy sources together and the customer's going to benefit from all of them, no customer wants to deal with all the different OEMs that provided that particular energy source, whether it's solar, batteries, gen sets. We pull all that together and then we make sure that that customer has one belly button, one owner of making sure that system operates as expected through its product life. We actually also do microgrid design modeling as part of every selling process. We'll talk about that a little bit later, but we do have some customers who aren't sure what they're going to do. So, for instance, a major medical chain in the United States, Kaiser Permanente, has us going through all their facilities where we look at almost all 100 of them have solar. How do we get better savings by expanding their solar? What would it take to do that? Batteries now are more cost effective, so they can provide significant impact when they're right sized. And how do we align those things and get them on the right utility rate structure? So we actually do modeling. We do modeling, for instance, for remote communities, and we can do those. And you'll see me give a case example why that modeling is really important before you make any buying decision. And we can offer, and not really a subject here, but in some cases, given the capital cost, some of our customers want to have financial options, and we provide that. Next slide. So the heart of the challenge of remote power really is embodied in this slide. As most people know on this phone, if not everybody, smaller the grid, the more you feel load changes, in a sense. So in a remote community, if there's, let's say there's one without, say, a fishery in it, they're kind of like larger grids. They're pretty predictable. Loads go up and down. Pretty gradually. Early in the morning, you'll see a rise. It'll drop off a little bit midday, and you'll see a bigger rise in the evening. You throw a fishery in that community, all of a sudden, if doesn't have its own power, now it becomes very volatile. A big piece of equipment gets turned on, and the whole community will see like a load spike when a big motor turns on. So smaller grids or microgrids have a lot of unique characteristics that large grids don't. So an example in the upper left of this slide, that's an actual 24-hour load profile of a factory that's off grid. and they literally see load changes within seconds that are 50% of their peak load. And you can see that in very clearly in that chart. Now you take some more dynamics that are very, very important to be able to understand and quantify. Solar is a lot more than volatile than say, hey, I got a cloudy day or I got a sunny day. Solar powered, many of you already probably know that a cloud comes over solar panels. You could lose 70, 80% of the power because of cloud cover. The cloud disappears and bang, it's back. And that can happen, especially many remote villages are especially remote applications are often along waterways or along, whether it's the Bering Sea or the Arctic Ocean or Hudson Bay. Obviously, wind cloud cover is very, very common and very, very just in and out. So this is an actual chart in the middle of the page of an actual solar output in a 24-hour period. This happened to be a solar farm in Florida. So that volatility is important. And oh, by the way, when the solar and wind go out, the gensets have to make up for that because suddenly the load is there. The gensets have to cut back. Suddenly it disappears. They have to ramp up. And we'll talk about the impact of that in a second. And within the genset itself, it only has so much time. They have a ramp rate. They have time it takes for them to respond, both up and down. And there's a mismatch between ramp rates and demand rates. And the bigger the mismatch, that's a whole nother problem. And by the way, natural gas, there's more and more communities, especially the larger ones, that are working towards getting or already have natural gas installation, or natural gas gensets to try to lower their power costs. But there's a impact of that because natural gas is just slower. So the more, say, solar and wind you have on natural gas fuel systems, the more volatile volatility you now are adding. So in short, you throw the load volatility, solar and wind volatility together, ramp rates of gensets, and controlling frequency and voltage becomes extremely difficult with traditional power systems, which have always been for 100 years synchronous gensets. So one other point about synchronous gensets, which many of you on the phone would be aware and some may not, synchronous gensets are forced to run at one speed to keep fixed speed, unlike your car engine. They can't run their engine speeds up and down as load demands go up and down because of what was created literally in 1890 by the real Tesla. They have to run at one fixed speed to keep frequency and voltage within limits. And then the way they adjust for power is they inject more or less fuel per cycle. So what happens is the more volatility in the system, the less capable they are to hold, in this case, frequency in this chart within specifications. And by the way, because of that, a lot of communities, or that anywhere where you have more than 20% solar and wind in your community, just with synchronous gensets, they can't handle anything more than that because they will destabilize the grid. And that's why many regions actually had restrictions on how much solar their communities can add to their grids because of this issue. Let's keep going. Next slide. So we call this, back a slide. So we call this concept of synchronous generation engine control power. It's been the same, as I say, for 100 years. So it's really the engine generator combination that's controlling the volume of power, speed of response to demand, and power quality, which specifically is frequency, voltage, and waveform. And so, and it's worked quite well. It's been a very simple system. The idea has been really very, very effective. It's very linear. Loads go up, more fuel goes into the genset. Loads go down, less fuel goes in. Everything is happy. But today you'll see why what Innovus has introduced is what we call grid genius or energy management centric power, which basically says, okay, instead of having the engine lock in at a set speed, either 1800 or 1200 RPMs in the US with 60 hertz, we basically say, we will basically allow the engine to do its thing. And what I mean by do its thing is we want the engine to always run at its most efficient speed. So like your car or a truck, we're going to run the speed of the engine up and down. And the implication of that is that now, wait a minute, what do we do with the power coming out of it because it's not usable? And I'll get to that in a second, but essentially this control of hardware and software, these control systems now control the volume of power, speed of response, and the quality of power. Go to the next slide. For any technical geeks in the group, and I and my Innovus team are part of that geek group. For anybody who wants to know how it simply works, essentially, if we're allowing picture in the middle of the block of slides in the lower part of the page, essentially, if we're allowing power to come out of an engine that's running at variable speeds, it means the generator is producing power at its frequency, which is unusable by itself. So we have to take it through a process of power conversion, and out spits three phase high quality power. So there's an extra step we have to add. So to allow us to harvest the benefits of running the engines at variable speed. There's also a benefit, which we're going to talk about in a few minutes, a huge benefit because it also makes the system far more compatible to adding solar and wind to these grids. It also has a huge impact in how powerhouses, which we're going to get to in a few minutes, and how powerhouses have been equipped through again, since the invention of electrification, where powerhouses are forced to use multiple gensets and multiple or larger systems if it's a larger powerhouse, so they can run it because they're only efficient at very narrow ranges. And again, we'll talk about that. So this has a big impact on what we would call simplifying powerhouses, which today are very, very complex. Next slide. The other way. I already showed this slide. Next direction. Next one. Oh, this one. I'm sorry. Okay. Yep. That one. So ultimately, the way we think about it is, it's really a hub and spoke, and you can read down the slide in terms of what the benefits are. We're going to talk about that a little more definitively in a few minutes. These systems are, of course, grid farming. It allows us to put a lot more into these systems that give, I'll call it monitoring of what's going on in a single box. There's just many benefits, which we're now going to cover. Next slide. So on fuel efficiency, I mentioned that there's big drawbacks to running synchronously, or what we also call fixed speed generators. So in a synchronous genset, which is the red curve to the right, because they're locked in, they can only run, say, at 1800 RPMs. They're most efficient when they're fully loaded. And you'll hear power experts talk about that. They want their gensets heavily loaded. And that's because they're most efficient in terms of fuel burn, whether it's kilowatt hours per gallon or kilowatt hours per liter for our friends in Canada on the call. You can see what happens with them, unfortunately, though, is as you look at the x-axis on the chart on the right, as the demand for power on that generator drops from 100% to 50% down to 0, there's a linear degradation of efficiency, or saying it a different way, there's more proportionate fuel burn, and at some point it literally drops off a cliff, starting around 50, 60%. And the reason that's happening is that when you're forcing an engine, which is really an unnatural act for an engine, it wants to run at variable speed to stay efficient. Because it's forced to run at a single speed, it basically can only adjust for power. Loads drop, so it needs less power. The only way to adjust for it when the engine speed has to change to stay the same is it has to inject more or less fuel per revolution. And that starts creating problems because as heat drops in the engine to drop power, so do gaps. And so gaps open up between pistons and cylinders. The same thing would happen if it was a turbine engine. So ultimately what's happening is you're starting to get losses as temperature drops. And at some point the gaps will get so large that you can literally get unburned diesel fuel dripping down the cylinders into the oil pan. And so that's why, for instance, every OEM, if somebody's going to run a diesel genset chronically below 35%, they won't guarantee the engine because it's doing damage. So not only is there a penalty on fuel efficiency, there's a huge penalty in maintenance. And anywhere along that curve, once it starts dropping off, yeah, all the maintenance cycles that are planned or recommended for these gensets are all based on this degradation of fuel, the average load that genset's going to run, and therefore, parts just wear faster. It's as I say, saying in another way, when an engine's run very efficient, it has the least wear on it, even though that may seem counterintuitive. Um, with a variable speed generator, because we're allowing the engine to run up and down in speed. It stays efficient from very high loads, and we don't even start to see a slight degradation, somewhere around 20%. It's just because at some point the heat drops a little bit, but we can run all day and night at 10 or 20% versus a synchronous genset. You can't do that. So it doesn't just have an implication on fuel efficiency. It has a huge implication on, well, how do I deal with it if I have a powerhouse where I'm supporting a community where its peak load in the wintertime is, say, 700 kilowatts, but in the middle of summer, its minimum load is 150 kilowatts. And I'll get to how they deal with it today, but there's huge implications because of how synchronous gensets are supposed to operate. There's also implications, of course, for anybody adding solar and wind to these systems, because again, by adding more and more solar and wind capacity, it's essentially pushing the synchronous gensets to a zone of loading where they don't want to be. They're just not happy there. And the more solar and wind you get to, the more problematic it becomes. And people have created a solution for that, which I'll get to in a number of slides, and still use them. And it's a viable solution. Again, I'll talk about it and where it actually makes a lot of sense. And that's where batteries start getting into the equation. But anyway, so it creates a lot of ancillary problems because we're forced to run synchronously, whereas in a VSG, we don't have to worry about it. So let's keep going. And now we'll talk about the powerhouses. So I was alluded to it before. You have a genset that's most efficient at its high loads, high demands. But what of course happens is loads, not just seasonally, but daily go up and down. They rise a little bit, as I said earlier, in the morning. There'll be a drop off maybe in the middle of the day and rise at night. Of course, the more remote, the more northern the communities are, we'll see, of course, a much bigger load in the wintertime than we'll see in the summertime. So utilities or operators of powerhouses have to figure out how to deal with that. So if you say, okay, well, I'm going to size the genset for my peak load, which may be 700 kilowatts in the wintertime, well, maybe I'll run chronically below minimums in the summertime, and I can't do that. And have those gensets be reliable. So what they'll typically do, as many of you on the phone know, powerhouse operators will have to put in 2 or maybe even 3 different gensets in their powerhouse. We've seen some even with 4, and they literally are turning them on and off during the day over a 24-hour period, depending on where the load profile is on that time of the day in terms of where it's hitting the sweet spot in a given generator. And of course, because you can't just turn one on and get beyond its capacity and turn it off and turn the next one on, you have an overlap, which is called the spinning reserve area. So when a genset gets above a certain load, they'll spin up the next genset to make sure if the load goes beyond its maximum, the next genset will pick it up, so you don't have an outage. But as you can imagine, well, now you're splitting the load. Now the load is being split amongst the 2 gensets. Now you're back into the lower loading situation. So it's kind of the best thing we can, that can be done. But you can imagine the complexity of a powerhouse that we've learned to live with for decades because of the realities of how synchronous generators operate. So ideally, it's kind of like saying, imagine if a car engine could only run one speed and every car had two or three engines on it, or every truck, and the engines get turned on and off depending on the load the truck is carrying and the terrain it's about to drive over. And powerhouses are forced to basically operate that way. And if we did that on a motor vehicle, because the engines could only turn at one speed, and we have two or three or four engines on it, we'd look at it and go, "Wow, this is pretty unwieldy." But again, it's been a necessary evil because of the way generation for electricity has to operate. So let's go to the next one. I talked briefly about the consequences of what happens when you start adding solar and wind to a grid. So what's happening with a synchronous generator on the chart on the upper left is that if you go, the y-axis is your levelized cost of power, which is including the cost of your capital equipment. So what's happening is, and I'm sorry, the x-axis is the amount of going from 100%, say, diesel, fossil power, to the far right on the x-axis is 100% solar and wind power. So at first you start adding solar and wind, and your cost starts to drop, as you would hope, because you're not burning as much diesel. But I alluded to a 20% law, because what happens is once you get to about 20% capacity of solar and wind capacity on that grid, the diesel gensets can't keep frequency within sound limits, and voltage starts to drift, and now you're risking an outage. And the reason that happens, I guess, for me, the best analogy I could use is everybody has speed cruise control on your car, and so you set it for 60 miles an hour, or Canada 100 I'm sorry, 100 kilometers per hour, and if you notice, if your terrain is flat, it stays exactly at the speed that you set. As you go up and down more steep and more rapid hills, or sharp, more steeper hills, you'll notice your speed is drifting up farther and farther away from, say, 60 miles per hour, or 100 kilometers per hour. And the reason for it is it's reacting. It doesn't know your car doesn't know you're about to be on a hill till you're on the hill. Now you're on the hill, it's trying to get more power out of the engine to get you back up to 60 miles an hour, so the speed drops temporarily. Then you go over the crest of the hill. Now you have too much power in the engine, and then reactively, the speed of the car, the computer's detecting, oh, I'm going too fast, I got to go pull back, fueling to the engine. So essentially, you're just drifting up above and below 60 miles an hour, and that's no different than what happens with a genset. So the synchronous genset. So the more solar and wind you put on your grid, that's essentially the same thing. You don't know it's coming till it's there, and now the engines or the genset's trying to react to a load change, and at some point above 20% of solar and wind, it can't keep within a very narrow, unlike your car, which can drift to 55 or 65 or 50 to 70 miles an hour, other than maybe getting a speeding ticket at 75. In a genset, where frequency and voltage have to be much more tightly controlled, now you got a problem and a risk of an outage. And so what happens is either people stop adding solar and wind to synchronous systems because they already know about the 20% problem, or if they didn't know about it, and that happened in many communities in Alaska 10, 12 years ago, they were adding more and more, say, wind power, and realized they had to curtail the power. You'll see a case example of that shortly. So now you add all that cost of generation, and now you're not able to take advantage of it, because you're having to curtail 60, 70, whatever percent of its capacity, because your synchronous gensets, which are controlling the power quality for that grid, can't stay stable. And so at some point, your cost of power starts to flatten out. In some cases, people have increasingly, and this is the solution to it that more and more companies or people have adopted, operators where they'll say, okay, let's throw batteries into the equation, which is a sound solution, but now you're adding costs to the grid. So the question is, we'll talk about that in a little bit more. Um, Depending on how much battery you add, it could either help the situation or it can inhibit at least the cost of power scenario. So with a VSG, and I'll explain why in a few seconds, with a VSG, essentially, or energy management controlled power, once you start adding renewables, the cost of power starts to drop, and it keeps dropping because we have no limit. We can take advantage of full penetration of solar and wind power without having the stability issues. We do have to add some amount of stored energy at 30% capacity, some cases 40. But then again, it's a lot less stored energy than you would have to add to a synchronous system. And again, I'll talk about that in the case example. Next slide. And here is the alternate solution. So the alternate solution is, in fact, so some operators will actually say, okay, I'm going to go add power converters to my synchronous genset because I already have to add some inverters for the solar power. I'm going to add battery inverters, and I'm just going to add a bunch of batteries, and basically the batteries everything becomes a battery charger. So to deal with all the volatility and everything else, the power out of the diesel gensets going into the batteries, the power out of the solars coming into the batteries, and then it goes through a power converting process and outspits AC power. A very, very good AC power, by the way. But the question then is, well, how much battery capacity do you need to add under that scenario? And you'll see in the next slide, it's not cheap. So yes, it's a functional solution. Yes, it works. And it's been proven it works. But there's a trade-off here. And generally speaking, because remember the synchronous gensets are inefficient at anything, once you drop below, say, 70 or 60% load. By the way, with natural gas, they drop off a table earlier than that. What they basically do is, they basically have to say, all right, if we're going to use the genset as a battery charger and run them at high loads, we're going to basically turn them on, run them out at full loads, and then the sizing of the battery bank really is determined by how often you want to turn the genset on and off during the course of the day and just run it all out so you recharge the batteries. So again, it's a solution that works, and there's certain scenarios I would suggest that it's a better solution than, say, what we would have where, we would have stored energy in a system to keep the grid stable, and then we'll have a certain amount above 30 or 40% capacity, and then there's a certain amount of stored energy we'll put in the system to better harvest the solar and wind power that's very spiky. You'll see a case example of that. But also, if we want to do extended engine off operations, which sounds at the surface to be the absolute way to go, and even then it is in many scenarios, but at some points, many communities, of course, use the heat from the engines for heating. So there's a trade-off on how much engine off operations do we want to go versus the benefits of actually their ability to deliver some level of heat. Next slide. And so when I mentioned a few minutes ago how stored energy has an impact, this is an independent study that shows the cost of different energy sources. And the great news is, depending on its scale, this chart is really more for utility scale. But the point is solar and wind have been dropping closer and closer and overlapping with the cost of fossil generation. Other than diesel, you see diesel, of course, which is the worst when it comes to cost per kilowatt hour. But stored energy can be just as costly. So it's very important that whatever stored energy is added to a remote grid, it has to be really judiciously added because there's a meaningful cost impact for it. So we when we do our modeling, pay very close attention to that. Next slide. Here's a wind case example of in the case of the left, this is an actual community that has a 700 50% kilowatt peak load. This was an actual study we did with that community, and we found that they had a megawatt of wind turbine capacity, and because of the instability issues at 200 kilowatts, they literally had to curtail the wind power. So those green the blue line represents the demand, the power demand over that period of days. The green lines represent the amount of wind power that was available in that moment of time. You can see how volatile it is, but you see it hits a ceiling at 200, not because the wind isn't there. It's because they had to curtail it to that point to keep their grid stable. And of course, the diesel genset's having to make up the difference. In the case example to the right, there's no VSG in this community yet. We did a study of this with wind and what would happen if we added solar on top of the wind. Basically, the 1 megawatt wind, if we didn't have to curtail it, it would basically be a 60% diesel reduction. And it would also be a meaningful maintenance reduction, cost reduction. Because again, you only have one diesel genset you're maintaining. It's running 24/7. We don't have to use multiple gensets in the powerhouse. And we're also not destabilizing the grid. We have some level of stored energy here, to make sure that that we also above 40% can keep the grid stable. We found in this particular community, if we added roughly 500 kilowatts of solar in addition to the wind already there, now we can get to an 80% reduction in the cost of power. That would include a right size battery system, because there also, you can see when the solar or wind exceed the demand, we want a way to at least capture and harvest it. And ultimately, the sizing of all this really has to be done community by community. We have to really understand the load in that community. The solar is a little easier to understand its availability. There's more public data available for a given geography. But once you start getting into wind, of course, we have to be very micro-focused in terms of not just what's available, but where that wind turbine would be. And again, everybody on this call clearly, I'm sure, understands that. Next slide. I'm not going to talk much about this. I think it's important once we talk about combining all these different energy sources. I touched on this earlier. Customers really want to know that somebody's paying attention to what's going on 24/7. So, for instance, that system that went into Klavic, as well with every other system we put out there, as an online monitoring system, we know exactly what's happening in the engine, the cooling systems, the power converters, et cetera, et cetera. So we get alerts if something looks like it's going haywire, or it could be a problem, so we can circumvent it. If there isn't a problem, we can assist the plant operators with, okay, you need to go check this, you need to go replace this. So it makes maintainability far an order of magnitude easier. We can also do remote upgrades of software from the field. Let's keep going. So basically summarizing, we can get to significant reductions in levelized cost of energy well above 50%. CO2 reductions, again, above 90%, including opportunities for engine off operations. And we're increasing reliability because and you'll see a case example in a couple of seconds, where the generators, because they're just happier running where they are, they wear less. The average speed, for instance, for the generators that were operating at Klavic, were slightly above 1,200 RPMs over a course of a year, whereas a synchronous generator would have to run at 1,800, 20, whatever hours it's operating from hell or high water. So just less revolutions per engine make them much more reliable and easier to maintain. Let's go. Let's keep going. Next slide. So here's a case example. I'll show you the results of a Klavic. Let's go next slide. And then there's a heavy industrial application that we've done. So in the case of a Klavic, in this case, we replaced 4 Detroit diesel S60 gensets that had been there. When I say replaced them, they went into reserve. They were then, and they weren't used in any 24-hour cycle. The only time they were used, they stayed in the powerhouse, is when the VSG was being serviced. So essentially, one VSG at 600 kilowatts replaced four Detroit diesels that were operating in that community. They also put some solar in place when we launched, and I believe the expansion went online last year for more solar. There's more coming online this year. Um, that system now is not operating, so I don't know exactly the status because they had to go. It exceeded its operating hours for the engine. They decided to go replace the engine, and they've been working to get that system back up and running. Next slide. Over 35,000 hours, which everybody on the phone knows is considerable. We had zero unplanned outages that caused community outages, which we're pretty proud of, are very proud of. So when people ask, are these systems reliable? Everything we use are proven. The engines are well established. They're Caterpillar engines or Cummins engines. They're the same engines basically used in synchronous gensets or traction operations. Those OEMs support those operations. The generators are the same generators, whether it's Cummins, Stanford. Um, we're literally using the same hardware that's well proven. The difference in adding the power converters, those power converters have been well established in industry for decades. So it's not a surprise if we use proven components that the system as a whole will be reliable. We had two unplanned shutdowns. Those both happened before when the system wasn't online. First was a software bug at engine startup. It was just data was being dropped and we had to reboot the system, eventually correct the software. That was accidentally dropping data. And the second was after, I want to say 4 years of operations, we noticed a coolant leak and there was an operating condition that had to be corrected. And that shouldn't happen again. Next slide. This simply says, look, the fuel efficiency was what we forecasted. The synchronous gensets that were already there the F60s were pre-regulated, unregulated units, so they're actually pretty efficient. They're actually very efficient. Most of our fuel savings were based on benefits in running in lower loads or avoiding having spinning reserve, multiple machine overlap. But also as they climb up the ladder on more and more renewables, then they'll really see the big benefits of the savings. Next slide. For the engineers on the phone who are on the call who are worried about power quality, regardless of load, we are dead nuts at 60 hertz. This happens to be 60.03 simply because they wanted a slight bias when we set it up, and that was intentional. But you can see how tight the power quality is, regardless of where the community is in its load profile. Next. This is a second case example. This was on a community. This is an heavy industrial application, a 1.7 peak load. I just quickly touch on it. And it was taken, they were running natural gas gensets trying to handle this transient. This application is really what proved what we call our power bridge feature, which integrates solar and wind. If you look at this load profile, it's more aggressive, far more problematic than, say, any volatility associated with solar and wind. And you could see the impact of frequency in the lower right when they were hitting these high volatile load changes. They would see literally a 700 kilowatt load change within seconds, and it would disappear. And this was just happening every day, and you can see the concentration. So highly problematic. And by the way, with a natural gas genset, which is slow to respond. Next slide. So in this case, we upfitted. We didn't. With natural gas, we don't really look at VSGs. We could, depending on application. We just haven't had a demand for it. There's benefits, there's trade-offs there, but really the value here was adding our energy management control system with rapid response stored energy, and you could see what happened to power quality in the lower right. So it went from outside of specifications. If this was a data center, those red lines represent the required power quality. So imagine you have a factory with forges and a bunch of heavy equipment running. And by adding our power management control system with energy storage, we went within specifications. And oh, by the way, we can run with a lot less gensets. Roughly, we went from 8 to 5. Next slide. The only thing I want to say on this slide and then get to now questions. Since we started out, we were roughly only doing 500 kilowatt gensets, 5 to 600 kilowatt gensets. Now with more engine options, and customers driving it, our Canadian systems going to the Canadian government. We'll have Caterpillar engines. Their next systems will likely be 340 kilowatt systems with Cummins engines. So we can now go as low as say 850 kilowatts, and we can go as high as roughly 2 megawatt single systems. One of our customers or potential customers is looking. Actually, one of our customers is looking to us right now, and they're thinking about a 1 to 1.5 megawatt single system to upgrade one of their powerhouses in one of their communities. And that's very doable. Next slide. Questions? Shemaine, I don't hear you.
Okay, can you hear me now?
Yes, I can.
Okay. I believe a question is coming in the chat from Richard Bailey. In the meantime, we did receive some questions via email. One of them being, how does Innovus figure out how to maximize renewable energy and minimize diesel at a given location?
So, Shemaine, I have to hear again. Hello? Okay, so we have to actually do would do a study of that particular community, to be able to figure out, what's the best combination and what's, of renewable energy sources in that specific geography. And what we would do is work with that customer, and we can give them because of our modeling capability, we would give them a whole range of choices. So we usually start with, information. What they most want to hear is, what does it take for me to basically eliminate, say, 90%, almost all of my diesel use? And we would get to a configuration, a capacity of wind and solar that's available in that particular location. And by the way, there's wind systems now that we are been looking very heavily at for especially remote applications that are much smaller and easier to install, 5 to 30, 40 kilowatt systems. And they don't need big foundations. But the point is, and you can service them on the ground, but the point is that we would maximize those, see what the right size stored energy would be based on their objectives, how many engine hours we need to run to support their heating needs, and we would come up with a configuration solution, cost of power as a result, and what the capital cost is. And generally from there, they will also say, or at the beginning, they say, well, we'd also want to see what would happen if we reduced it by 50% or 70. And then they can start to see the trade-offs between, getting to that goal as compared to how much it would cost in capital and installation costs to be able to get there. So that's generally how we approach it. So I hope that answers that question.
So the next question, okay. The next question from Richard is, are VSG systems compliant with emissions regulations?
Yes, they are, with an asterisk. In Canada, they are, because in remote locations, we can use Tier 2 engines, and all of Canadian operations, we could use Tier 2 engines for all their rural or remote applications. So we're emission compliant there. In Alaska, they're running on waivers and been for many years, because Tier 4 engines have FCRs that that most people who know the Arctic know they can't work up there. So they do allow Tier 3 marine engines. We can use Tier 3 marine engines for our VSGs in Alaska, and they would be compliant. The asterisk is VSG or Tier 3 engines only go up to 750 kilowatts, 750 horsepower. So we can only get about 450 kilowatts out of those. To go higher, we'd have to get them to approve using Tier 2 engines. Frankly, I think with the emissions reductions, we just never approached them because there hasn't been a demand from a utility yet that causes us to trigger that discussion. But I think all we'd have to do is show them the significant impact on fuel and emission reductions. When I dealt with the ADEC in Alaska and EPA, they're generally pretty very reasonable to deal with. And I think if they saw a solution like this, they'd have no problem jumping into Tier 2. But obviously, I can't guarantee that. Next question. Next question.
So Jonathan Linton is asking, he's stating that problems that has been raised to him on reserve are power outages and power quality, resulting in premature failure of electronics. Your system addresses this? If so, could you elaborate a bit?
Yeah, I'll start with power quality, and I touched on I talked about this earlier because all the because the power quality is being literally controlled and driven by power converters, the same type of power converters that you would use on a solar and wind installation. Um, the frequency and voltage stays very tight. We can send anybody asking this question. We can actually send a demo of the systems we sent to Canada for the Canadian government last month, of the first of of two systems, and you can see literally we can throw a step change of 100% on a step load of 100% on the engine, and and power quality is just it can handle it. It was stunningly good, which no community would ever see. As far as failures and premature failures, it goes back to the same issue talking about earlier. I mean, running an engine at one speed is not a natural act for a piston engine. They don't want to run that way, but they're forced to run that way for power generation purposes. And as I said, to control, because they're the ones that have to control power quality. And when you think about it, just like there's a linear relationship in degradation of efficiency. I would argue that there's a relationship in reliability, because the more you're operating at low loads, and it's very hard to predict how long you're going to be there because it's a daily event. Because powerhouses are running on multiple machines, now it's a powerhouse operator or a PLC for some, which is very hard to program to work properly. You're trying to predict when the next loads are going to go beyond your capacity, and therefore they want to turn another gen set on early, and now you're having the loads of both, and both could be running lightly loaded for continuous hours. And by the way, if I was a powerhouse operator and I was making these decisions, I know I would probably get fired if my community goes out or a power, so I'd rather run the generators asynchronously. I'm sorry, I'd rather run more generators than I need and burn more fuel and get my risk slapped, and maybe run into more maintenance issue, which is tomorrow's problem, than not have power today. One other comment on the outages are because a lot of these areas, more and more people are adding solar and wind to these grids, which I touched on, that now we can be hitting into that stability issue. So people, of course, they're putting, in businesses or homes, they're putting more solar into the grid, which is tied back to the utility grid. So that number keeps creeping up. So I'm guessing, depending on the community, that's also could be a contributor to outages, because if the stability goes above, or instability goes above a certain limit, then what's going to happen is the system protects itself and you end up with an outage. So everything points to the wrong dynamics as we want to get deeper and deeper into renewable power and tying them to synchronous generators.
So,
I
Omar,
think I have time. Go ahead. Go ahead.
I think we have time for one or two more. On that note, how long have the core technologies of the VSG platform been operating to validate their reliability?
Great question. Obviously the engines, these are, as I said, these are the exact same engines that have been used in whether it's traction or generation applications. So, and they're standard. So we're using a standard CAT or standard Cummins, could be NTU, depends on what the customer requests. So, I think that's easy to answer. Millions of hours, or maybe even billions, of field service over the years across God knows how many applications. Generators are the same thing. We're using the same generators that you would use in synchronous generators. Um, the power converters are a more recent technology, but more recent says maybe 20 years, 25 years. So use of power converters has become more and more common as solar and wind have become a bigger part of the landscape. So even those systems have probably now millions of hours on them. We happen to use now Danfoss power converters in our system. Everything we're using has been well proven in similar applications. One last question, or we're out of time.
Okay, I think we have time for one more question. Again, this one came from someone via email. They want to know what are the biggest challenges in adoption.
I think the biggest challenge is it's just, given how critical power is in all these remote applications, people understandably are extremely conservative. In many products, it's like, how many have you sold? Well, I've sold this many, or we've sold this many. Okay, I'll buy one. Um, or okay, where do you have one installed? Well, we have them installed here and here. Well, okay, man, that would satisfy most products. Well, do you have one operating? Yes. The long and short of it is in this um, uh, segment, people want to know not just how many you have, but how long you've been operating, what the issues have been, and it just takes a long time. So it took 4 years to get our first sale of a VSG, and the systems that are now going to finally to a point where we demonstrated with enough application experience that it was Ameresco that bought the systems that are going to the Canadian government, and they're highly reputable as an EPC. And the Canadian government had to approve the use of our system in their remote location. I can't talk about where it is and what it does. All I can say is it's a damn critical location. And so it just takes years. But I think fortunately, when people who have, studied it for a long time are convinced that now we're starting to see people moving in that direction, saying, yeah, this is the right way to go in the future. So I want to thank everybody. I know we're out of time. I apologize for probably taking a lot more time away from Q&As than I had planned. Uh, Please feel free to send Shemaine will send an email out. If you have other questions that you want to ask that you just ran out of time, we'll answer them. And we just look forward, we see this as a start of a discussion for whatever organization you're a part of. Shemaine, you have anything? Thumbs up, thumbs up.
Yes, I am typing your email address in the chat right now, and we will be sending out this recording to everyone. So please feel free to share and look forward to seeing you at the next one. Thank you very much. Give everyone a chance to look at the email. Bill is typing something, Mark.
I'm saying a scale source of Sandy Thompson asked their question about the. So I'll just answer that in an email. Unless Sandy wants to stay on it, she's still on.
Bill is just thanking you.
Sandy, if you want me to answer the question now, you just send a confirmation on chat and whether you want to stay on and let's go down and answer it.
Okay.
Okay, I still see Sandy on.
Yeah,
So,
as he speaks.
I think Sandy the he, I'm not sure. So, Shemaine, can you mute again because we're getting feedback?
Okay, of course.
Hydro turbines. Like, I'm looking at Sandy's question.
Yeah. Can you hear me, Mark?
Yes, I can. Yeah, I'm not sure I have.
It wasn't really a question. It was just an endorsement of your principle because we're manufacturing hydro turbines and we use exactly the same principle of generating variable frequency AC, converting it to DC, and then transmitting it to the powerhouse as in a DC line, and then the powerhouse going back into synchronous AC.
Oh, that's great.
Because and the reason we do it that is because there's a certain speed that we don't have to worry about. We can maintain efficiency of the turbine if it can run at different speeds. It doesn't have to run at a single speed. Whereas if it's synchronous, it has to run at a given synchronous speed.
Yeah, it's interesting. I took a tour of a with a river hydro turbine operation not too long ago, and yeah, he said, yeah, no, we have to force it to run at one speed. And here's all the consequences of that.
The other thing I would endorse is the fact that this whole process takes a long time. It's just something you adopted.
Yeah, do you mind me asking where are your turbines operating today?
Well, we're manufacturing them in Poland. We have 2 of them in operation, and we're putting a 3rd one into Temiskaming Shores in Northern Ontario in Canada.
Oh, super. Yeah, the last river, I didn't realize river hydro, or I'll call it small river hydro, was viable until it was a big thing until I visited Cordova Electric. I've been there twice. So Cordova has a number of hydro turbines out there, and are you familiar with them?
Yes, not well, but I know them. Yeah.
Yeah. So their CEO is Clay Copland, very into if he worked he'd be a big advocate for what you're doing. I'm not sure if he needs any help right now, but he's always out in front of this stuff. But he's kind of one of those he's one of those early adopter type guys, but of course they have to be proven.
For sure.
But
what's his name again? What's his name?
Clay. I'll send you an email with this contact information.
That's perfect. Send me an email.
Yeah, he's a great guy. We haven't even sold a product there because because they need diesel generation to back up the hydro, and they have a unique problem because they have fisheries there. They have quite a bit of fishery demand, and you can imagine how volatile that is.
Oh yeah, that's a side consideration.
So he's also, by the way, the mayor of Cordova. So he'll definitely give you he'll give you the time of day.
Good enough. Send me his coordinates. I'd be pleased to receive them.
Well, thank you for attending, and we'll stay close.
Fair enough. Good enough. Great presentation. I've enjoyed it. Thank you.
Thank you. All right.